In this video, we will learn when to perform a hypothesis procedure for one or two tail tests, to define the significance of a p-value, to analyze the statistical significance, and to criticize the reported p-values. Let's start by summarizing the results that we have until this point. Let's assume that we have a large sample and the mean is defined by mu and the standard deviation for sigma. So we are interested in testing the null hypothesis, and the null hypothesis can have three different forms. Either mu is less or equal to a given value, mu is greater than or equal to a given value, or mu is equal to a given value. So we have either inequalities or equalities. The next step that we have to do is to compute the z-score for the mean of the sample. And if we don't know the standard deviation of the population, we approximate that with the standard deviation of the sample and divide by the square root of n. Next, we need to compute the p-value, and the p-value is the area under the normal curve and depends on the alternative hypothesis. Let's consider the first case when mu is greater or equal to a given value. In that case, the area that we need to compute is the area on the right. So that corresponds to that case. In the second case, the alternative hypothesis mu is less than a given value. So this is for the second case. And the third case is the equality condition for the alternative for the null hypothesis, and that will be the non-equal for the alternative hypothesis. In this particular case, we need to consider both sides, the ones on the left of c and the ones on the right of negative c, or the complement of the other one. So this is a two-tail and corresponds to the non-equal alternate hypothesis or equal null hypothesis. We have two possible conclusions from the hypothesis test. Either we reject the null hypothesis, in other words, we conclude that the null hypothesis is false and therefore the alternative hypothesis is true, or we do not reject the null hypothesis. In other words, we conclude that the null hypothesis is plausible, and in this case we cannot conclude that at H1 the alternative hypothesis is true. In either case, we can never conclude that the null hypothesis is true. We need to know what level of disagreement measured with the p-value is great enough to render the null hypothesis implausible. The smaller the p-value, the more certain the null hypothesis is false. The larger the p-value, the more plausible the null hypothesis becomes. But we can never be certain that the null hypothesis is true. As a rule of thumb, we reject the null hypothesis whenever the probability is less than 0.05 or 5%. This rule is convenient but has no scientific basis. Let's consider the following examples. In the first case, we are looking to the efficiency of electric motors. We have a sample of 65 elements with mean equal to 0.595 and a standard deviation of 0.05. The motor efficiency population mean needs to be less than 0.6. So this is the alternate hypothesis. So therefore the null hypothesis is that the mean is larger than 0.6. So let me highlight here the null hypothesis. So because the sample mean is 0.0595, so that's the value that is located in that point, 0.595. It's actually in agreement with the alternative hypothesis, so we can't accomplish the test. So we need to compute the area underneath that part of the normal curve, and when we do, we find out that this value is equal to 0.2, so it's 20%. We can see actually this is actually close to 0.6, meaning that because this value is larger than 5%, it's possible that the result that we have, 0.595, is a random variation, and the mean is probably in this region. So in this case, we cannot reject the null hypothesis. In the second case, we have a corrosion test. The sample is equal to 60, and the mean of the sample is 150 and the standard deviation 153. In this particular case, we are looking for the specification that says that the population mean has to be larger than 900 micrometers. So again, this is the H1, the alternative hypothesis, and we need and the null hypothesis, it will be that mu is larger than 900. So let me highlight here the null hypothesis. In both cases is in the same side, but when we compute the probability of 850, which is the value in the sample, we can see that the area underneath the curve is much more smaller with respect to the problem before. So in fact, and that is equal to 0.0057, which is much less than 5%, and therefore we can reject the null hypothesis, and the alternative hypothesis is true. So the population mean depth is less than 900. Statistical significance. Whenever the p-value is less than a particular threshold, the result is said to be statistically significant at that level. So if p is less than 0.05, the result is statistically significant at the 5% level. And if the probability is less than or equal to 0.01, the result is statistically significant at the 1% level. If the test is statistically significant at the 100 alpha level, we can also say that the null hypothesis is rejected at the level 100 alpha %. In general, when we use the alpha term, we are referring to a fraction which is in between 0 and 1. For example, the hypothesis test is performed on a null hypothesis, mu equal to 0, and the p-value is equal to 0.03. 0.03 is 3%. Question: is the result statistically significant at the 10% level, at the 5% level, at the 1% level? Well, because we obtain 3%, we can say that it is statistically significant at the 10% level, at the 5% level, but not at the 1% level. The second question: is the null hypothesis rejected at the 10% level, the 5% level, the 1% level? We can affirm that the null hypothesis is rejected at the 10% level and at the 5% level, but we cannot say that the null hypothesis is rejected at the 1% level. How should we report the results of a hypothesis test? Well, sometimes people report only that the test is significant at a certain level without giving the p-value. For example, the result is statistically significant at the 5% level or statistically significant at p less than 0.05. This is generally not a good idea for three reasons. First, it provides no way to tell whether the p-value was just barely less than 0.05 or whether it was a lot less. Imply a big difference between a p-value just under 0.05 or just above 0.05. A report like this does not allow the readers to decide for themselves whether the p-value is small enough to reject the null hypothesis. So in general, it's a good idea to report your values and let the reader to make the conclusions based on the information that you are providing. Reporting the p-value gives more information about the strength or evidence against the null hypothesis. The bottom line, the p-values should always be included when a hypothesis test is reported.